Have any questions? And then today we're going to continue the discussion, and we are going to talk about the applications of transducer system. Well, passive application is typical example of a passive application is a sensor, and active application is the control of chemistry. Okay. And transducer action here, we are talking about is a chemical energy and electrical energies. That is the transducer actions. And for example, the fuel cell is irreversible reaction, and the batteries, it can be reversible. Here in the battery case, we call the charge discharge, right? Charge discharge. So let's start with the applications of free energy of formation of a phase. So the system is going to be, for example, X2 gas we have a system, something like this. Then here the electric potential is related to the chemical potential. And then the gives free energy for formation mx is going to be equal the chemical potential, and that is equal to chemical potential of X2 in this fashion. Okay? For example, oxygen case psi equals GF. And then number 2, measurement of activity of a species in a solid solution. That we have discussed, which is Nernst equation, okay? Nernst equation. So here the Nernst equation is RT ZF, activity of species and diverse species and the two electrons, something like this, okay? And number 3, partial pressure measurements. Partial pressure in a gas phase. Here we have air and zirconia and PO2 gas phase. So we want to measure the partial pressure of oxygen in this closed system with this sensor, okay? And this is the yttrium stabilized zirconia. We usually use the yttrium stabilized zirconia as a oxygen conductor. If you set that, then the EMF, the voltage that we measure, is going to be related to the partial pressure of oxygen in air and the partial pressure of oxygen that we are interested in to measure. And partial pressure of oxygen in air is about 0.2 atom, right? And G is equal to -4. And this thing can be used as an oxygen pump or oxygen sensor. This is an active application, and this is a passive applications. Okay? And we have discussed about the coulometric titration curve, the equilibrium properties. Number 4, electrochemical titration. The current is going to be ZQJ, right? The flux. And if we have a system Mx and Mn, N1 plus delta M plus delta N by passing current. Here the delta is going to be I is going to be I dt over ZFN, okay? Total charge and number of For example, if you have a half gram of sample, which is related to 10 to minus 2 moles, okay, and Faraday constant is 9, and Z is equal to 1, and let's say the current is 10 to minus 6 amps, and T is 100 seconds, for example, then ten to minus 6, 10 to minus 2, 10 to the 5th, and 10 to minus 2, with 10 to minus 7 as 4 delta. That's that's very big number, right? So we can control the chemical reaction in a very precise manner. Fuel cell or batteries. This is a convert chemical energy to electrical energy. So if you have M plus, and Mn system like this, here the potential, the voltage that we measure is the electrical potential difference. And then is related to the chemical potential. And that is concentration of species M in Mn, right? So in this fuel cell or battery systems, conductivity of ions or diffusion coefficient of M in Mn, okay, in electrolyte. Both these two terms are important. Okay, and especially the diffusion coefficient of M in NM. This is a solid state. So this is usually the liquid system. So this is very important. Usually have a small number for the diffusion coefficient of the electroactive species, right? But we can have a high conductivity or diffusion coefficient in some special cathodes, Mn, for example, interstitial anion matrix, which is AgI, copper bromide. In this case, we have excuse me. We have a matrix like this, and then we have almost a liquid state, but it's a solid, the molten salt. We have very fast silver ions conducting in this AGI system. Or we can have tunnel structure. Are you going to have a 2N or 1N in the tunnel? 1N? 2N? Okay. Tunnel structure. Like a potassium tungsten oxide and sodium tungsten oxide. And in this system, it has something like this. Okay, open structures. So we have oxygen octahedrons, and our tungsten at the centers here. This is the oxygen framework, and we have a potassium in the hexagonal tunnels, very wide open, and then lithium ions can go into this open structure through this hexagonal tunnels. It's like a freeway. Okay, then sodium almost has the same structure, and here the potassium has to be replaced with the sodium, and it's very high lithium-ion conductors. Okay. And also we can have two-dimensional open structures. Two-D open structure. And that is beta alumina. That is a typical example. And this is a sodium ion conductor. In beta alumina, there is a whole blocks, and the blocks in between we have a two-dimensional space, and here the sodium ions can travel through this two-dimensional open structures. Okay. something like this. We are going to talk about the fast ionic conductors later, at the very end of this class, okay? And number 6, maximum theoretical specific energy. Or watt-hour per kilogram, something like that, okay? We can have this. And if we have a lithium and lithium-ion conductors and aluminum, and we are going to insert the lithium into aluminum so that we are going to make LiXAl system like this, okay? And for this lithium conductors, we usually use LiCl and KCl salt, which is a high lithium ionic conductor at the temperature 400 degrees centigrade. Not at room temperature, but at this temperature, it is a very high lithium ion conductor, so that we can draw derive the specific energy system of this system, and like a coulometric titration, you're going to have alpha phase, that is lithium, and the LiXAl, and we have a plateau here, and then we're going to have lithium, aluminum, single phase, and then we have Li3Al, single phase, something like this, okay? And this is alpha, and this is beta, and this is gamma phase. It's more or less a coulometric titration curve, right? And then we can have specific energies for each plateau. And the kinetic, we also carry out the kinetic measurements. And the first thing is going to be supersaturation for nucleation of a new phase. And the example we are going to have here is the nucleation of silver from silver sulfide. So that is AgI superconductor for silver, and then we have silver sulfide, and here at this interface we are going to blow H2 to control the to control Ag to S ratio. Okay, if you blow the H2 at elevated temperature to the Ag to S, then the S is going to be reduced so that we can have increased the H to S ratio. And then with the different ratios, then we have a different potential between these two, so that we can measure, if we measure in this system the potential, that is the voltage, we're going to have some curve, something like this, and that this overshooting is related to the super saturation potential. Okay? And another kinetic measurement example is the rate of motion. That is the growth rate of an oxide layer on metal, for example. And the system is going to look like this. We have air and zirconia, again, the oxygen conductor, and we have a system for ion interfaced with FeO by exposed to the carbon oxide system, gas mixture. Then basically what we are doing here is that we are going to have a moving boundary problem here. Moving boundary. And we have ions. We try to oxidize the surface of the ion with this gas mixture, and then we're going to create FeO on top of the Fe, right? And then this, as the oxidation process proceeds, this moving boundary is going to move into this ion, and then eventually all the ion is going to be transferred to the FeO at the end. And for these moving boundaries, we're going to have different voltages between this air and an oxygen to sensing the oxygen content in this ion cathode. Okay, so if you measure the voltage in that case, you're going to have some FeO, in a solid solubility limit. We're going to have a supersaturation, and here the plateau is Fe and FeO two-phase regions. Okay? And then after everything is turned into the FeO, we are single-phase regions, so that we are going to have another slope here, and then we end up with the plateau again, and this plateau is FeO and the gas mixture equilibrium. Okay, so this is the time that required to oxidize all of the Fe to convert Fe to FeO, right? So up to here, time necessary to transform all Fe to FeO. So in this example, oxidation rate is controlled. By oxide gas interface. Reaction. And not by auto diffusion. In FeO. So you use all different thickness of Fe and then make the surface to be oxidized with the gas mixture, and then measure the time T1 with a different thickness. Okay, this is the T1 and this is the Fe thickness. And then you measure the T1 time there, then you might have some curve like this, and then you can solve the moving boundary problem. With this, you can see the velocity of this moving boundaries in the ion and FeO. Then you can have kinetic data out of that. The important thing to notice here is that this moving boundary is not controlled by the diffusion of oxygen in the FeO, but controlled by the surface reaction at the ion and FeO interface here. The chemical reaction controls everything, not the diffusion of the electroactive species in the cathode. And the final example that I want to introduce is the interface reactions. If we have a system like M anode and then electrolyte Mx and the system My, and then at this interface we do the evaporation, for example, so that we control the My ratio in this cathode. Okay, then we can measure the voltage and if we assume that M is moving relatively fast inside the My so that we always can have equilibrium My inside the My. and there's no concentration gradient of M due to high diffusion coefficient. Of M. Then we can see that the chemical potential of M and the M, of course, is a pure material, and in the Mx and My here, inside the My at T1 and T2 and T3, inside the My, it's equilibrium always obtained because the high diffusion coefficient of M inside this. And Mx, maybe, this is not a straight line, but it should be connected to this. Actually, this does not have to be linear. But we can see the interface reactions by monitoring the chemical potential, which is again related to the electric potential, the voltage of the two electrons. Okay, this is the example of how we can use the transducer system, electrochemical system, to measure the various properties, and then that is related to the active applications and passive applications. So it is a very powerful method. Before I leave this section, leave this chapter, let me just introduce what we have to think in the defect equilibrium diagrams. Okay? Say practical considerations. Practical consideration. And defect equilibria. We have defect equilibrium diagram like this, and then we have two cases, Ki greater than Kd or Ki less than Kd. Okay, electronic, this is electronic material, and this is ionic material, right? And well, this is these are the major defect concentrations. So we can notice that the minor change in F composition, the parameter, may result in rapid change from electronic conduction to ionic conduction. That's a very interesting fact, okay? This is the log F, and then see the major defects is the electrons and defects here, and then if it is electronic ionic material, in this case, in this range, we're going to have major ionic conductors. So, before this value of F, we are electronic conductors. Even though the concentration of electrons and ions is almost the same, the mobility of the electrons is much, much higher than the ionic species, so that we can say this is the electronic conductors. But if we change the value of F, compositional parameter F, then this material, electronic conducting materials, is going to transform into the ionic materials. Because the electron, you have a very much low concentration of electrons, even though the mobility is higher than the ions. See, this is the log scale, okay? Log scale of the concentration. So this sharp decrease in the concentration makes this system ionic conductors. So this just reveals the fact that the minor change in F may transform the electronic conductor to the ionic conductions, or ionic conductor to the electronic conductions, things like that, okay? How do you control the composition parameter F? Composition parameter F. How do you control the composition parameter F? Well, just to give you the example, the oxygen conduction through oxygen vacancies, okay? And I should write the oxygen vacancy is going to be doubly positively charged defects, because the oxygen itself is a negatively charged species, and if you have a vacancy of it, the lack of minus charges is going to be the plus charges. So vacancy of oxygen will have the positively charged like that. And then this oxygen can be conducted through this vacuum site and yttrium stabilized zirconium. Yttrium stabilized zirconium, right? And ITO, indium tin oxide, transparent electronic conductor, transparent electronic conductor. If it is transparent like a glass, it just means that we have a band gap too large, so that electron transfer from the valence band to the connection band is impossible. That's what the transparent material, right? So it cannot observe the light. So that is a transparent. And so normally the glass is not a conducting material because it has a too big band gap. But in case of ITO, you are going to put the indium 3+ and replace it with the tin, which is the 4 plus. Okay, so that you can create the positively charged vacancies, which renders the electrons corresponding to compensate that substitutional replacement, and then that is the free electrons and free holes, which is conducting, which is working as a conductor. That is the indium tin oxide. Okay, indium is basically indium oxide In2O3, and some of the indium is going to be replaced with the 4 plus, and then 3 plus is replaced with a 4 plus, so that every single replacement will render 1 electrons to neutralize the system. And that electron is used as a free carrier for the conductors. And that is what the ITO. The same thing happens in the zinc oxide. In this zinc oxide, you're going to have a zinc vacancies, which is related to the free carrier generation, and then that is going to be used as a conducting material. Okay, so zinc oxide and ITO are two major materials to be used as a transparent electronic conductor, and that is very, very important in the flat panel display devices, all the display devices. Okay, lastly, we have electrochromic system. One, two, three. Electrochromic system. Electrochromic system. For example, potassium tungsten oxide. If you insert the lithium into this, then it's going to be colored. Okay, depending on value of X. It's going to be the color intensity is going to be changed, and we call that electrochromic. Okay, it's exactly the same way to show the color changes, but the oppositional way is the NIO system. NIO is originally colored deep blue, but if you put the lithium into this, so that you form the LiX Ni2O, then is bleached. This material is colored deep blue. Okay. So if you want to have an electrochromic system, then what you are going to have is that one side here is the potassium tungsten oxide, and in this side you are going to have a NIO, okay? And then you originally put some amount of lithium into this, so that this is a cathode, and this is going to be the anode. Okay? And then here you have a lithium ionic conductors, then what you can have is that by putting the lithium from this material to this material, then this one is colored, and then if you take out of the lithium, this one is going to be colored. Okay? If you put the potential such that you move the lithium ions from here to here, then you're going to, this material is going to be bleached, and if you add the lithium into the NiO, then this one is going to be colored, bleached again. So we are going to have a bleaching reactions, electrochromic reactions. So this is a novel method to make an electrochromic system, to put the two materials, electroactive species, electrochromic materials together and utilizing the effects like this. And by making the solid state for the lithium ionic conductor here, if you can make it, then you can make all solid system, and we call it a curtainless window or smart glass. Then this is going to be used, for example, if you have a room for this, and then you have an electrochromic system like this, and then if you have this many people in one room and you want a privacy, and then you color only this part of the electrochromic glass, okay? And then if you need, you want to extend it, and then you just bleach this, and then you color this. And then we call this a curtainless window, smart glass. This is not industrialized because we do not have a fast ionic conductor of the electrolyte yet, but I believe it's going to be industrialized soon. Right now, the smart glass uses the LCD system. Okay? So it contains the liquid electrolyte. Okay, on Wednesday, we're going to talk about the thermodynamic quantity determination by the electrochemical system. And then next week, we're going to discuss about the kinetic measurements with the electrochemical system. And as I told you just a minute ago, it has a very high precision. So it is a very powerful technique to use the electrochemical system to determine thermodynamic properties and the kinetic properties and so on. Okay? And I'll see you guys on Wednesday then.